Hi, welcome to this video on energetics for CSEC Chemistry. These are your typical exam questions. You should be able to distinguish between exothermic and endothermic reactions, draw energy profile diagrams to illustrate endothermic and exothermic change, and calculate energy changes from experiments or from experimental data. Now, in a chemical reaction, there's always going to be some sort of energy change in the system. This is either going to be energy given out to the surroundings or energy taken in from the surroundings, and that's usually in the form of heat. In other instances, for example, when you see fire, it's going to be in the form of light. But in the context of energetics or CSEC chemistry, we're going to be looking at how heat is given out or absorbed. You should recall that in a chemical reaction, what you're going to have is bonds in the reactants being broken and bonds in the products being formed. Now, when you have those existing bonds in the reactants being broken, energy is required. You need to take in energy, absorb energy to break the reactant bonds. When bonds are formed in the products, energy is released, so you give off energy. Now, a chemical reaction that produces heat, which causes the reaction mixture and its surroundings to get hotter, is an exothermic reaction. In these reactions, energy is released to the surroundings. For example, neutralization reactions, respiration in cells, and burning fossil fuels. So, in an exothermic reaction, energy is released to the surroundings because the energy that is released when forming bonds in the products is greater than the energy absorbed to break bonds. So, if you have more energy being given off when bonds are formed in the products, than you have energy being taken in when bonds are broken in the reactants, obviously there's going to be a net giving off of energy. That is the characteristic of an exothermic reaction. And that extra energy is released to the surroundings, which causes the temperature of the surroundings to increase. Conversely, a reaction that absorbs heat, causing the reaction mixture and its surroundings to get colder, is an exothermic reaction. And in these reactions, energy is absorbed from the surroundings overall. Endothermic reactions include plant photosynthesis and thermal decomposition. So the energy absorbed to break bonds in endothermic reactions is greater than the energy released when forming bonds. So it's the very opposite of the exothermic reaction. If you have more energy being needed to break bonds than energy released in forming bonds, overall, you're going to have energy being taken in, being absorbed. And that extra energy that's needed that's needed to be absorbed is taken from the surroundings, which causes the temperature to decrease. It's important to note, however, that for both exothermic and endothermic reactions, while we said, oh yes, in exothermic reactions, energy is released, and in endothermic reactions, energy is absorbed. That is in terms of an overall basis. Energy is released and absorbed in each of the reactions. It's just that one, whether it's released or absorbed, is higher than the other. Either you're releasing more or you're absorbing more. When you're releasing more energy than you absorb, that's going to be an exothermic reaction. When you're releasing less energy than you absorb, or you're absorbing more energy than you release, that's going to be an endothermic reaction. Now, there's this term called enthalpy, which is basically the energy content of a substance. Enthalpy is the energy content of a substance, and it's represented by the letter H. The thing with enthalpy is that you can't measure it directly, whereas you can say, oh, temperature, let's take this thermometer and say, oh, it's 37 degrees Celsius. You can't measure enthalpy directly. It only has meaning when there's a change in a given system. Now, the enthalpy of a reaction is equal to the enthalpy of the products minus the enthalpy of the reactants. And we're going to see how that falls in shortly. So remember that we said for an exothermic reaction, energy is released. So as you can see here, you have the reactants yielding the products and energy is released. Now, by the law of conservation of energy, since energy is neither created nor destroyed, and that means that the total energy is the same on either side of the arrow. So the total energy of the reactants has to be equal to the total energy of the products and that extra energy you give off. Therefore, the products have lower energy than the reactants. In an exothermic reaction, the enthalpy of the products is less than the enthalpy of the reactants, as you just said, because the enthalpy is the energy content of a substance. And because of that, delta H is just negative, because as we said, the enthalpy of the reaction is the enthalpy of the products minus the enthalpy of the reactants. And if the enthalpy of the products is smaller, then you're doing smaller number minus a bigger number, which is going to give you a negative. Therefore, delta H is negative. Now, since the enthalpy change is a change in a substance energy content, and we just said that the reaction loses energy or energy is given off, the enthalpy change is negative. So it makes sense both ways when you think about the products and the reactants, and when you think about the energy content or the overall reaction losing energy. An endothermic reaction, on the other hand, can be described as reactants plus energy yielding products. And because of the same energy neither created nor destroyed, both sides of the equation, that means that the products have higher energy than the reactants. That's why in an endothermic reaction, the enthalpy of the products is greater than that of the reactants, which makes delta H positive. Or you can also think of it as since the reaction is gaining energy, the enthalpy change is positive. So what the most important thing that you should get from that is that in an exothermic reaction, delta H is negative, and in an endothermic reaction, delta H is positive. For example, the combustion of methane on the left is an exothermic reaction. The value of delta H is negative, and that indicates that 891 kilojoules of energy is lost when 1 mole of methane is completely burned in oxygen. On the right, an an endothermic reaction is being observed, and the positive 26.5 kilojoules per mole indicates that 26.5 kilojoules of energy is made when 1 mole of hydrogen iodide is made during the reaction. The overall energy absorbed by this reaction in particular, represented in the equation, would be double this value because 2 moles of hydrogen iodide is being made. And note, in a reversible reaction, if the forward reaction is exothermic, the reverse is endothermic, and vice versa. For example, when nitrogen reacts with hydrogen to form ammonia, delta H is negative 46.1 kilojoules per mole. So that means that the forward reaction that produces ammonia is exothermic because delta H is negative. The reverse reaction is endothermic, and that means that 46.1 kilojoules. You're also required to know energy profile diagrams. Now, the energy changes that we've been talking about in these calculations can be represented on graphs that they do ask you to draw. And those graphs are energy profile diagrams. They show the enthalpy of the reactants and products, the change in enthalpy, the activation energy, which is the minimum quantity of energy needed for the reaction to occur, and yeah, that's the energy profile diagram. And it's important to note, however, that the amount of activation energy does not affect the overall energy change and so is not included in the calculation. So for the exothermic reaction, the enthalpy of the products is less than the enthalpy of the reactants. And that difference in the lines between the products and the reactants, that is where you're going to label your negative delta H for an exothermic reaction. For an endothermic reaction on the right, the enthalpy of the products is greater than the reactants. So that difference in the line is going to be your positive delta H. Your activation energy is a line that moves from the reactants line to the very peak of the graph. However, you're not going to include that little bit of activation energy in the delta H calculation. Now, you should recall from rates of reaction, if you've covered that topic, that a catalyst is a substance which alters the rate of a chemical reaction without itself undergoing any permanent chemical change. Now, you have catalysts that speed up reactions, and these catalysts provide an alternative pathway which requires less activation energy than the normal pathway. Again, catalysts that speed up reactions say, hey, here's another pathway for your reaction. And this pathway actually requires less activation energy. And you want to do what's energetically favorable. So, in reactions that are sped up by catalysts, the alternative pathway that requires less activation energy is taken. Although the reaction has a lower activation energy, the energy values for the reactants and the products remain unchanged. So delta H is unchanged as well. So you do need to know how to label the energy profile diagram with and without a catalyst. So for a catalyst that speeds up a reaction, obviously the energy content needed for the reaction to proceed, i.e. the activation energy, is going to be lower. That's the case for both exo and endothermic reactions. And this topic also involves calculations. So as we said, enthalpy cannot be directly measured, but the change in enthalpy can be determined by measuring the heat of reaction, which is, as you may have guessed, the heat change occurring during a reaction. That's calculated by measuring the change in temperature. Additionally, to calculate energy changes, it may be necessary to know a substance's specific heat capacity, which is the quantity of heat required to raise the temperature of a unit mass of a substance by 1 degree Celsius or 1 Kelvin. For example, the specific heat capacity of water is 4.2 joules per gram per degree Celsius, which means that it takes 4 joules of heat to raise the temperature of 1 gram of water by 1 degree Celsius. Now, if you know the mass of the substances as well, then you can calculate the heat of reaction from this equation. The heat of reaction is equal to the mass times the specific heat capacity times the change in temperature. So delta Q, which is the heat of reaction, is equal to mc delta T. Heat of reaction is typically measured in joules, mass in grams, specific heat capacity in joules per gram per degree Celsius, and change in temperature, obviously, in degrees Celsius. And to determine the heat of reaction, the reaction is carried out in a calorimeter, which is an insulated container that prevents heat from being released to the surroundings or gained from the surroundings. A simple calorimeter can be made out of a polystyrene cup. Or your styrofoam cup. So you have your styrofoam cup, the chemical reaction takes place inside the styrofoam cup, and that reduces the amount of energy that is exchanged with the surroundings. The general method for determining heat of reaction involves measuring a fixed volume of solution or water to be used in a measuring cylinder, pouring it into the calorimeter, and measuring the initial temperature using a thermometer. You then mix the reactants in the calorimeter and measure the minimum or maximum temperature reached in the reaction. Then you calculate the temperature change and use mc delta T to calculate the heat of reaction. Importantly, there are three assumptions that are made in calculating the heat of reaction. They have asked you to give these three assumptions before. You need to know them. One is that the density of a dilute aqueous solution is the same as that of pure water. That is 1 gram per centimeter cubed. Two, the specific heat capacity of a dilute aqueous solution is the same as that of pure water, i.e. 4.2 joules per gram per degree Celsius. And three, a negligible amount of heat is lost to or absorbed from the surroundings during the reaction. Heat of solution. So when a solid, liquid, or gas dissolves in a solvent, there's usually a change in enthalpy. And the heat of solution, by definition, which is something you do need to know, is the heat change occurring when 1 mole of solute dissolves in a volume of solvent such that further dilution by the solvent produces no further heat change. Now, when your solute dissolves in your solvent, you're going to have bonds between the particles of the solute breaking, which causes energy to be absorbed from the surroundings. For ionic compounds, the ionic bonds break, and with covalent compounds, the intermolecular forces break. Now, the intermolecular forces between solvent molecules also break, which causes energy to be absorbed. And finally, attractions are formed between the ions or the molecules of the solute and the molecules of the solvent, and that's called solvation, which causes energy to be released. This is all to say that that's where the energy absorption comes in to play, and that's where the energy being released comes into play. Now, if more energy is released during solvation than is absorbed to break the bonds in the solute and solvent, then the reaction is exothermic, as we said earlier, because that would mean that more energy is released than absorbed. And of course, the opposite for endothermic reactions. So calculating the heat of solution, you need to know the initial temperature and the exact quantity of solute dissolving so that you can calculate the number of moles. For example, dissolving 15.15 grams of potassium nitrate in 100 centimeters cubed of distilled water results in a temperature decrease of 10.2 degrees Celsius. Calculate the heat of solution of potassium nitrate. So we're going to calculate the number of moles of potassium nitrate first. Now the molar mass of potassium nitrate is going to be 101 grams per mole, and moles is equal to mass over the molar mass, which is 15.15 over 101, which gives you 0.15 moles. The volume of water, we're told, is 100 centimeters cubed. The mass of water is going to be 100 grams because of that assumption, because we're assuming that the density of this dilute aqueous solution is the same as that of pure water. So that means, which is 1 gram per centimeter cube. So if you have 100 centimeters cube of water, that means you're going to have 100 grams of water by that assumption. Therefore, the final mass of solution is going to be the 100 grams of water plus the 15.15 grams of potassium nitrate, which is going to give you 115.15 grams as your final mass. And we calculated the number of moles, so we can therefore calculate the heat of reaction. Q is equal to mc, delta Q is equal to mc delta T. So the 115.15 grams times the specific heat capacity of water, which we're assuming is the same as the specific heat capacity of this dilute aqueous solution, times 10.2, which we're given in the question, temperature decrease, is going to give us 4,933 joules, which we're going to convert to kilojoules, which is 4.933 kilojoules. Now, it's important to note that this calculation that we have right here, this 4.933 kilojoules, that is the heat absorbed in dissolving 0.15 moles of potassium nitrate. So now we have to calculate the heat absorbed in dissolving 1 mole of potassium nitrate. And you can do a simple cross multiplication for that. If 0.15 moles produces a heat change of 4.93 kilojoules, then 1 mole produces 32.9 kilojoules. Just add multiplication, divide 4.93 by 0.15. And the heat of solution is hence 32.9 kilojoules per mole. And what's very important is this plus sign. And we know that is positive because we were told in the question that it was a temperature decrease. And we know that a temperature decrease means that energy overall was absorbed, which means that it's an endothermic reaction. It's important when you're writing your final answer to take note of what it tells you in the question. Because if it says that the question results in a temperature increase, when you're doing your calculations, you're not going to be taking that into account unless you put the negative in there. Just make sure that in your final answer, you have positive if it's endothermic or negative if it's exo. The other type of calculation that you can be asked to do is heat of neutralization. We know what a neutralization reaction is. Acid plus base gives you salt plus water. And the neutralization between a strong acid and a strong alkali is exothermic. Now, the heat of neutralization, the definition, is the heat change occurring when 1 mole of water is produced in a reaction between an acid and an alkali. Now, when you're calculating that heat of neutralization, you need the initial temperature of both solutions, average them, and use that value as your initial temperature. And you also need the number of moles of water produced. For example, a volume of 50 centimeters cubed of sodium hydroxide of concentrations 1.0 moles per dm cubed and temperature 26.0 degrees Celsius is added to 50 centimeters cubed of hydrochloric acid of concentration 1.0 mole per dm cubed and temperature 27.0 degrees Celsius. After mixing, the maximum temperature of the solution is 33.2 degrees Celsius. Determine the heat of neutralization for the reaction. It's always useful to write out your reaction equations so that you know your molar coefficients. So you're going to have sodium hydroxide reacting with hydrochloric acid to give you sodium chloride and water. The number of moles of sodium hydroxide made is going to be 0.05 moles. Now we're told that it is 50 centimeters cubed of sodium hydroxide solution of concentration 1.0 mole per dm cubed. So from moles, we're going to get 0.05 moles. And we note that the mole ratio between NaOH here and water is 1 to 1. So therefore, we know that 0.05 moles of water is produced. Alternatively, you could calculate the moles of HCl and do the same calculation. As long as you're able to calculate the number of moles of water, which is what you need, then you're good to go. Now, the volume of solution is going to be those 50 centimeters cubed of each solution, and they sum to give you 100 centimeters cubed. And by the density assumption, the mass of the solution is hence 100 grams. We averaged the 26.0 and the 27.0 to get 26.5 degrees Celsius as our initial temperature. We're told that our final was 33.2, so the temperature change is going to be 6.7 degrees Celsius. Now, the heat involved in forming 0.05 moles of water is going to be 100 grams times the 4.2 joules per gram per degree Celsius times the 6.7, which gives you 2,840 joules. The heat evolved in forming 1 mole of H2O then is going to be 2.814 divided by 0.05, which gives you 56.28 kilojoules. And again, heat of neutralization. The reaction is exothermic, so we're going to have a negative in front of our final value in kilojoules per mole. If you don't have the negative, then it's wrong because you're suggesting that the heat of neutralization is endothermic. Remember to include your signs in front of your values. Now, if you do a heat of neutralization reaction between a strong acid and a strong alkali, it's always going to be around that value, around 56 or so. That's because strong acids and strong alkalis are fully ionized in aqueous solution. The common reaction is going to be the hydroxide reacting with the hydrogen ion, forming water. That reaction has an enthalpy change of negative 56.3 kilojoules per mole. The equation for the neutralization reaction between sodium hydroxide and sulfuric acid is as follows. In this reaction, you can see that 2 moles of water is produced, but the heat of neutralization is still going to be about negative 56.3 kilojoules per mole. However, the overall heat change of the reaction is going to be double that, because as we said, the heat of neutralization is for 1 mole of water being produced. And since 2 moles of water are produced in this reaction, it's going to be double that. You can also determine the heat of neutralization from the results of a thermometric titration. If you don't know what that is, you should head back to acids, bases, and salts. But in that method, you're going to take the initial temperatures of the acid and the alkali, you're going to measure them, and then the point of intersection between the two lines on that graph of best fit is going to be the maximum temperature. Exam style questions, the ones from earlier, well, let's do the structured question first. Distinguish between the terms endothermic and exothermic. Generally, when chemical reactions take place, existing bonds are broken and new bonds are formed. Classify bond making and bond breaking as either endothermic or exothermic processes. Easy 4 marks. So distinguishing between endothermic and exothermic, during an exo whoops, during an exothermic reaction, more energy is released during bond forming than is absorbed when bond breaking, and therefore heat is released. Therefore, the temperature of the surroundings and the reactant mixture increase. And the very opposite for endothermic, more energy is absorbed to break bonds than is released to form bonds, and therefore heat is absorbed, which means that the temperature of the surroundings and the reactant mixture decrease. That is more than enough for the 2 marks. So, and of course, bond breaking is endothermic and bond making is exothermic. Just like that. Which of the following diagrams best illustrates the course of an exothermic reaction? Remember that we said for an exothermic reaction, the enthalpy of the products is less than the enthalpy of the reactants. And the only one there is going to be A. So the answer is A. The figure below is a diagram of the enthalpy change for an exothermic reaction, showing the effect of a catalyst on the reaction pathway. Identify the parts labeled A, B, C, and D. So we know that A here is going to be our activation energy, but that's also B. So the difference is that A is the activation energy without the catalyst, and B is the activation energy with a catalyst. C we know is the change in enthalpy, delta H, and D is the products. So A, energy activation energy without catalyst, B, activation energy with, C, enthalpy change, and D, the products. When heat is given off to the surroundings during a chemical reaction, it is because bond breaking, A, releases energy as well as bond making, B, requires less energy than is released when new bonds are formed, C, requires more energy than is released when new bonds are formed, or D, is an endothermic process, whereas bond making is exothermic. So we're talking about bond breaking here and why heat is given off to the surroundings. And we know that bond breaking is an endothermic reaction, whereas bond making is an exothermic one. However, we're talking about when heat is given off. So therefore, we need to make the distinction that when heat is given off, i.e. an exothermic reaction, bond breaking requires less energy than is released when new bonds are formed, i.e. overall energy is released. So the answer for that is going to be B. What D is saying is correct. Bond breaking is an endothermic process and bond making is an exothermic one. However, it's even more important to note that the question says when heat is given off to the surroundings. So you can't say it is D. And now an exam question. This is from January 2018. When a reaction is accompanied by energy changes, it can be categorized as either endothermic or exothermic. Distinguish between those terms. We saw that question already, so we know. Generally, when chemical reactions take place, existing bonds are broken and new bonds are formed. Classify as endothermic and exothermic. As we said earlier, bond making is exo and bond breaking is endo. In an experiment, when 12.0 grams of potassium nitrate is dissolved in 100 centimeters cubed of water, the temperature drops by 4.20 degrees Celsius. Calculate the number of moles of potassium nitrate used in the experiment, given that the RMM, the relative molecular mass of potassium nitrate is 101. So, easy one, Mark. We know that moles is equal to the mass over the molar mass, and that we're given that as RMM here. So that is going to be the 12.0 0.0 grams divided by the 101 grams per mole. 12 divided by 101 per my calculator gives me 0.119. I believe that it would be perfectly fine to put 0.12 moles. Easy one, Mark. Calculate the heat change of the reaction. So we know that the heat change is going to be mc delta T. They already give us this assumption and this assumption. So, well, we already given the values for those assumptions. So we know that our mass is going to be that 12.0 plus 100 centimeters cubed of water. Now, I just want to make sure because there is a little bit of ambiguity here, but for this, you should use 112, the 100 centimeters cube of water plus, well, the 100 grams of water, because we're given that the density of water is 1 gram per centimeter cube, plus the 12.0 grams of potassium nitrate. Some say that you don't use the 12 grams of potassium nitrate, you just say 100 grams of water. But what CXC has in their subject report is that it should be 112 grams. I'm reading from the subject report now. I'll put it on screen. In this question, it is assumed that the specific heat capacity of the solution is the same as specific heat capacity of water. This assumption is acceptable for dilute solutions. And it is to be noted that M, which is the mass of the solution, is the mass of water plus the mass of salt. 100 grams plus 12 grams is 112 grams. In some instances where the mass of the salt is much less than the mass of the water, the mass of solution can be assumed to be equal to the mass of water. The accepted answer is the heat change is equal to 112 grams times the 4.2 joules per gram per degree Celsius times 4.2 degrees Celsius, because that's what we're told the temperature change is, which is going to be 1,976 joules. And hence calculate the enthalpy change for 1 mole of potassium nitrate. Now, if we knew that the enthalpy change for 0.12 moles, as we calculated earlier, was 1,976 joules, and the enthalpy change for 1 mole is going to be 1,976 joules, and let's just convert that to kilojoules so we have our answer. So 1.976 kilojoules over 0.12 moles will give us, per my ability to calculate, I hope, 16.5 kilojoules per mole. And then, as we always do, we note that the temperature drops by 4.20 degrees Celsius. Therefore, it's positive. So we can leave it by that, but just to make sure, let's put our positive there. So the next question asks us to list 2 pieces of apparatus necessary to conduct the experiment in a school lab and state how each piece is used. So as we looked at earlier, you're going to have our styrofoam or polystyrene cup, insulating container or calorimeter, and of course our thermometer for measuring heat change. Easy 4 marks. And finally, draw a labeled energy profile diagram to represent the enthalpy change for the reaction. On your diagram, indicate the sign of delta H for the reaction. So let's draw up our axes for this question. Here we're going to have the energy content or the enthalpy, and here we're going to have the course, well, let me say the progress of the reaction. And it is an endothermic reaction, so we know the enthalpy of our reactants is going to be less than the enthalpy of the products. Let's draw our line and a little dotted line across here. So here we have our reactants and here our products. The activation energy is going to be the entirety of this here. And our delta H is going to be positive. Don't forget that delta symbol there. Just like that, well, drawn with a ruler and in legible handwriting, 3 marks for a total of 15 marks for this question.